Okay guys, in the last video we discussed about central tap full wave rectifier. This was the circuit diagram. We discussed it in detail, and these are the input signal. So here we have the input signal, and the output signals are given here. This is omega t. Like if positive half cycle is reached to the primary coil of this central tap transformer, then D1 become forward bias, D2 become reverse bias. So D1 allow the current to flow through this circuit A, B, F, C and F through this loop. And if negative half cycle of this input voltage, input signal reach to this primary coil, then D2 become forward bias and D1 become reverse bias. So the output current, output voltage drop across this voltage can be measured, which is due to the flow of current through this loop. So here we have this output signal, input signal. Its maximum value or the peak value is represented by Vm. Here we have both positive and negative half cycle, but once it passes through this central tap full wave rectifier, then we have this shape of this output signal. Here this is due to D1, because D1 is forward bias and D2 is reverse bias, so D2 has no function in this positive half cycle. So we have this one. In the next negative half cycle, then D2 become forward bias while D1 become reverse bias. So this output is due to D2, while D1 is reverse bias, so it does not allow current to flow through it. So the current is flowing through D2. And also it is unidirectional, because in both the cases current flew from E to C. It's a unidirectional. This is the summary of the previous video, and this video we will discuss the average load voltage. Average load voltage. But it's the average DC, because we have the DC load voltage. The average load voltage is normally represented by VAV, where V, this capital V for voltage and this AV is for the average. We simply write it as VDC voltage. VDC. So average is basically the DC voltage, and we have a formula that the average voltage, the average DC voltage through the load resistor is equal to, which can be calculated from this plot, which is the area under the curve divided by base. Now we have the periodicity is from 0 to pi. In the full half wave rectifier, the periodicity was from 0 to 2 pi, because 0, pi, 2 pi. So the periodicity was this one. But here the periodicity is this one, 0 to pi. So the base is 0 to pi. And we know that we have the output voltage V0. Its value is Vm sine omega t, where omega t is less than pi and greater than 0. That's its value is Vm sine omega t between pi to 0. So this is the period. Now if you calculate the average voltage VAV, or the DC voltage DC, which is equal to area under the curve, which can be obtained, I already mentioned it in the full wave half wave rectifier, which is equal to integral of V0 into d omega t divided by base, which is pi, while the limits of the integral are from 0 to pi. In the half wave rectifier it was from 0 to 2 pi, but here it's from 0 to pi because the periodicity is from 0 to pi. Then pi to 2 pi again we have the same shape, so it's the 0 to 2 pi. Now we have this value for the average voltage. So it means that the average voltage will be equal to VAV or VDC is equal to integral from 0 to pi. This pi I will bring it outside, 1 over pi. 0 to pi we have V naught into d omega t. This is equal to 1 over pi integral from 0 to pi, and we already mentioned here that V naught is Vm sin omega t. Vm sin omega t to d omega t. Omega m is Vm is also constant, so keep it outside of the integral. We have Vm over pi integral from 0 to pi sin omega t into d omega t. Now we have to solve this integral, which is Vm over pi. If I integrate this sin omega t, we get minus cos omega t, and the limits are from 0 to pi. So this is equal to Vm over pi into minus cos of pi minus into minus cos of 0. So this is equal to Vm over pi minus cos of pi is equal to minus 1. Then we have minus into minus cos of 0 is minus 1. So this is equal to Vm over pi, and we have here this is 1 and this is plus 1. So we have 2 Vm over pi. The average or DC voltage, V average of VDC, is the value which is given here. While in the case of, this is for the full wave rectifier, while in the case of half wave rectifier, we calculate the average voltage of VDC, which was pi divided by, Vm divided by pi. So it's the double, 2 times the average voltage of half wave rectifier. Next we will discuss about average DC current. Average DC current. Average DC current. As we know that average voltage is equal to 2 Vm over pi. Let's say this is equation 1. Also we know that from Ohm's law, V is equal to IR. This implies that I is equal to V over R. So I average, which is equal to basically, which is the DC current, IDC, which is equal to V average divided by RL, where R is the load resistance. Where R is the load resistance. This is the Ohm's law, and from this we got I is equal to V over R. If I take the average, then I have the average here and I have the average here. So the average current is equal to average voltage divided by load resistance. But average is also represented by IDC. So this is the DC current. Next, we will move to calculate its value now. The value should be, let me fix the page first. The value should be like this. I average or IDC is equal to V average. So instead of V average, I will put 2 Vm over pi. 2 Vm over pi divided by RL. This is the load resistance. So I average is equal to IDC, which is equal to 2 over pi, and we have Vm over R here. Now Vm over R is basically, by Ohm's law, V is equal to IR, I is equal to V over R. So Vm over R is equal to Im, maximum current. So it's equal to 2 over pi times Im. We can write it as 2Im over pi. This is the average current, IDC. While in the case of half wave rectifier, the average current was IDC was Im over pi. Again, the average current is twice the average current of half wave rectifier. This is the value. We can also calculate this value by using the formula I average IDC is equal to area under the curve divided by base, because we have the output and input voltage current. This is the input current I. This is the I maximum value of current, and here we have omega t. This comes from, and we have the output current, which is like this. This is omega t, and we have output current is this one, I naught, and this I naught is equal to Im sine omega t for omega t less than pi and greater than 0, because this is the period. 0 to pi is the period. 2 pi, 3 pi, 4 pi, and so on. 0 pi, 2 pi, 3 pi, and 4 pi, and so on. So if we calculate, put the value in this formula, we have base is 0 to pi. This is the period is pi. The base is pi, while the area under the curve is started from 0 to pi. So the integral is from 0 to pi, and we have I naught, the value of I naught, times d omega t. So this will be equal to 1 over pi, integral from 0 to pi. I naught is Im sine omega t into d omega t. This is equal to 1 over Im is also constant, so I can keep it outside of the integral. Time Im over pi, and we have integral from 0 to pi sine omega t into d omega t. Now this is equal to Im over pi. If integrated, we get minus cos omega t, integral from 0 to pi. If I put the limit and solve it, from this we get the value 2. So give a value of 2, so we have 2 Im over pi. This is the average current, it's the DC current. So we calculate two values in this video. One is the average voltage, okay, the average voltage VAV, which is also called DC voltage, which is equal to 2 Vm over pi, and we also calculate the average current, which is also called the DC current, which is equal to 2 Im over pi. In the next video, we will derive some other factors relating to this full wave rectifier. Thank you.